Hi friends, I hope you're doing great. IBM is here. I'm doing very well, and I hope you're also doing very well. I know some of you could be in holidays. Please enjoy your holidays. Your physics companion is here to bring you an episode or the first episode of electricity, that is going to be electricity and DC circuits, or DC circuits involving Kirchhoff's laws and so on and so forth. So I'm not going to waste much time, but if you're new to this channel, please consider subscribing. If you want the past paper documents, just go to the video description. They have been attached in the video description. Click on the links, and the documents will open automatically, and they will be ready for download. The documents are entirely free. They are entirely free. So today we are going to start episodes of electricity. Electricity is going to be one of the most complex units, because it will require a lot of understanding, application of knowledge, and being able to conceptualize or to manipulate the ideas you have learned and put them into solving past paper questions. So here you must be very careful. Sometimes the solutions will be longer because this part of the syllabus is a little bit technical, but of course I know at least by the end of every episode you'll have learned something. Without wasting time, let's go to the document and start solving the past paper questions. So here we are. So this is, it's supposed to be unit 8. It's supposed to be unit 8, but I'm not solving them in the order of units because my students suggested that I solve the most important topics first. That's why we did waves, and now we are dealing with electricity. After electricity, then we shall have enough time to do the short topics. Okay, number 1, a length of wire RS has circular cross section. At end R of the wire, this side here, the cross section is A. At end S, the cross section is A/2. Charge Q takes time t to pass through end R. So at end R, it takes time t. There is a constant electric current in the wire, so the current is the same. So if the current is the same, we can begin with the concept of the current. I want you to recall that current is equal to never, or N A Q V. My students, instead of writing Q, they prefer to write E, and they simply write current as equal to never. That is another equation for finding current. So since the current is the same, we also know that the charge is going to be given by IT. But before we do that, so the current this side R is supposed to be number of charge carriers. The cross-section area here is A, and the charge of each charge carrier is Q. The drift speed this side I'll call it V at position R. I'll do the same thing the other side. The number of charge carriers is N. The cross-section area is A/2. And the charge of each charge carrier is Q. The drift speed is V. I'll call this one Vs. So if the current is the same, then these two expressions are going to be equal. So that means we shall simply say that V at position, current at position R is going to be the same as the current at position S. That means NAQVR is the same as NA/2 QVS. So Q cancels, N cancels, Q cancels, A has cancelled. And you notice that Vs, if I make Vs the subject, is going to be twice Vr. So the drift speed at S is twice the drift speed at R. In fact, the drift speed is inversely proportional to the cross-sectional area. If the cross-sectional area has been halved, then the drift speed must double. Okay, so if we know that, then we go back to the expression for V for current equals to V over, current equals to Q over T. So we are going to find the current, the charge at R. The charge at R is equal to Q, is given as Q, because it is given at Q, as Q, then Q is going to be equal to the current I, then times the time T, that is at R. And if we substitute, or if we put in our concepts here, you'll also notice that this is going to be the same as the current, which is given as, which we have got as N A Q, drift speed at R, then times T. That is the current there, that is the charge there. What has been given as Q. Then the charge at S, similarly, is going to be current again, which current this side is going to be N A over 2 times Q times the drift speed Vs. This time, the time is T over 4, so this is going to be times T over 4. So this is times T over 4. So we are going to combine these two equations. Remember, the charge at R is Q, which is given as that. The charge at S, I'm calling it QS. Remember, Vs is the same as twice Vr. So we're just going to combine these two equations. So QS is also going to be equal to N A over 2, then times small q. Where there is Vs, I'm going to put there twice Vr. So this will be times twice Vr, then times T over 4. So you can now divide the two equations. This equation here divided by that equation there. So you have QS divided by Q. This is going to be equal to, without wasting time, when I divide, I'm just going to cross out the terms which cancel. So because I'm dividing, N cancels with that one, Q cancels with that one, VR, of course this 2 has cancelled, VR cancels, and this T cancels. So we have remained here with, we have A, have maintained A there deliberately, divide by, this side we have A divided by this 4 here, so that is A over 4. That is A over 4 is in the numerator. A over 4 is in the numerator, and then in the denominator it is going to be A, because we are dividing the second equation by the first equation. So this leaves our ratio as QS is equal to Q times, because A has cancelled, that is times 1 over 4. So our answer is going to be Q over 4, which makes our answer to be option B. So this is A over 4 divided by A, which is 1 over 4, then times Q, that gives us Q over 4. Okay. Power supply is connected to a component by connecting wires of total resistance 9.4 ohms. The power supply has an output of 3.6 volts and a terminal PD of 12 volts. 3.6 watts output and a terminal PD of 12 volts. How much thermal energy is dissipated in the connecting wires in a time of 1 hour? So we know that energy is equal to power times time. The time is 1 hour, but power dissipated is equal to I squared times R. Then I'll multiply this by 2. The only thing I need to find is I, because I have R and I have T. All I need is I. So from power equals to IV, from power is equal to IV, for a power of 3.6, I is, this is going to be I times 12, which means that the current I is going to be equal to 3.6 divided by 12. And I think this gives us 3.6 divided by 12, that is 0.3. So the current is 0.3 amperes. So it means energy is going to be I, which is 0.3 squared, times R, which is 4.9, then times T, which is 1 hour, that is 3,600 seconds. So this is going to give us 0.3 squared times 4.9 times 3600, and that gives us 1587.6 joules, which is the same as 1.6 kilojoules. So our answer is going to be C. A copper wire is to be replaced by an aluminium alloy with an alloy wire of the same length and resistance. Copper has half the resistivity of the alloy. What is the ratio? Diameter of the alloy over diameter of copper. So we know that resistance is equal to rho L over cross-sectional area, and the area is pi d squared, which makes this to be 4 rho L divided by pi d squared. I've just got area being equal to pi d squared over 4. When I substitute, the 4 goes up. They have told us the resistance is the same and the length is the same. So I'm just going to come up with two equations for simplicity. For the first one, a copper wire is to be replaced by an aluminium alloy. Let's start with the copper wire. The resistance of the copper wire will be equal to 4 times rho. The copper has half the resistivity of the alloy. So if the resistivity of the alloy is rho, then the resistivity of copper is going to be rho over 2. Rho over 2, then times L divided by pi d for copper. I will call it d copper squared. That is for copper. Then for the alloy, I will call it resistance of the alloy. It is going to be 4. Because the resistivity, I've called it rho, its length is L. The diameter, we don't know, let's call it d of the alloy. So this is going to be pi d alloy squared. Remember, the resistances are the same, so I just equate the two equations. So I'll simply say that 4 rho over 2 times L, the length is the same, divided by pi d of copper squared is going to be equal to 4 rho L over pi d of the alloy squared. So I will cross out some of these things which are identical. 4 cancels, pi cancels, L cancels. So I remain with rho over 2. Rho over 2, this is d copper squared, is equal to rho over d alloy squared. So rho has cancelled, of course, rho have cancelled, but I want diameter of the alloy over diameter of copper, so I'll just cross multiply and make diameter of the alloy squared over diameter of copper. These ones are squared, should be equal to, the other side I have twice rho divided by rho, which shows that rho cancels out. Then I have to find the square root. So diameter of the alloy divided by diameter of copper is going to be the square root of 2. So which makes our answer to be A. Three identical filament lamps P, Q, and R are connected to the battery of negligible internal resistance. Okay, they are identical, so that means we can say they have the same resistance. The filament wire in lamp Q breaks. So the filament, this one breaks, so that means it is out, so that it no longer conducts. Okay. The filament wire in lamp Q breaks so that it no longer conducts. What are the changes in the brightness of lamps P and R? So to understand this, let's give these lamps some resistance that we shall base on. Let's say they both had resistance 2 ohms. They all had resistance 2 ohms. It means here, when they are in parallel, total resistance here would be 1 ohm. And total resistance here is still 2 ohms. If the same current is flowing through this combination, it means the PD here is higher. The PD across this lamp is higher than the PD here. Now, if this breaks, so that the 2 ohms is no longer there, it means the resistance remaining here is only 2 ohms. And if the resistance here this resistance here is now 2 ohms, it means the PD across this lamp should increase. And if it increases, it means the PD across this one should decrease. It will be a value less than it was before. Because now they are going to share the EMF equally, since now the resistances are going to be the same, and they will be as if they're in series. So this one is going to be brighter than it was before, and this one is going to be dimmer than it was before. So the PD across P is going to increase because the resistance has increased. The PD across R is going to be decreased. Therefore, P is going to be brighter than it was before, and R is going to be dimmer than it was before. So P is brighter and R is dimmer. So the answer is going to be B. Which ratio has the same units as EMF? The same units as EMF. We know that EMF is work done per unit charge. And this gives us the units as joules per coulomb. So which ratio has the same units as electromotive force? Number one, charge per unit energy transfer, that is coulombs per joule, that is not true. Charge per unit time, that is coulombs per second, that is not true. Energy transferred per unit charge, energy is in joules, charge is in coulombs, so the answer is C. A circuit consists of a battery, a voltmeter, and 5 fixed resistors as shown in the figure there. The voltmeter reading is 0. What is the resistance of resistor R? I want you to look at this pattern and remember your teacher must have said that this is a Wheatstone bridge. Whenever you have such kind of arrangement, it is called a Wheatstone bridge. And if a Wheatstone bridge, the PD across 2 points in the diagonal here is 0, if this is reading 0, the potential difference between those 2 points is 0, then it means the crisscross relationship will be valid. The crisscross relationship is valid only if the voltmeter reading is 0 between a circuit like that one, like the Wheatstone bridge there. If the voltmeter reads 0 here, it means the potential at this point is the same as the potential here. That means the product of these two resistances is going to be the same as the product of these two resistances. This is what we call the crisscross approach. The crisscross relationship. So what I'm saying is very simple. We are going to check this. These two are going to give us 2 times 10 should be equal to, remember these ones are in parallel. This combination is in parallel, which gives us 8 times R over 8 plus R. Because they are only 2, their resultant is product over sum. So this is going to give us the product here. This is going to give us 5 times 8R divided by 8 plus R. That is, the resistance here is the product times the resistance here. This part here should be equal to the resistance here times the resistance here. So we try to solve this. We can try to solve this. So this is 20 divided by 5, which is 4. So we shall say that 8R over 8 plus R is equal to 4. Simplify further, 8R is equal to 4 times 8, that is 32, plus 4R. So collecting like terms, 4R is equal to 32. And precisely this gives us R as 8.0 ohms. So our answer is going to be D. Remember the crisscross approach on a Wheatstone bridge is only, this is called a Wheatstone bridge. Wheatstone bridge. If you do this in the laboratory, you realize that the crisscross relationship applies. You adjust the resistances until the PD across them is 0. You notice that the product of the resistor you have put here and the other one there will be the same as the product of the resistor you have put here and the other one there. That is if the voltmeter gives a 0 reading. A battery of e.m.f are 6 volts and negligible internal resistance is connected to voltmeter and 4 other components as shown. The voltmeter is connected between points X and Y. The positive terminal of the voltmeter is connected to X and the negative terminal of the voltmeter is connected to Y. Initially, the resistance of each of the 4 components is 1 kilo ohm initially. So let's say this is 1 kilo ohm, 1 kilo ohm. These two are in series. If it is initially 1 kilo ohm, they divide this equally. So this gives us 3 volts. This gives us 3 volts. The PD across them. This will also be 3 volts. This will be 3 volts initially. Which change on its own will cause the voltmeter to show a positive reading. So if the voltmeter is to show a positive reading, then current should be flowing in that direction. The current is supposed to be flowing in that direction. That means the potential this side should be higher than the potential the other side. So the question is, which change on its own will cause the voltmeter to show a positive reading? So we want the potential this side to be higher than the potential the other side. What should we do? If I consider these 2 points, the potential here is 3 volts, so the potential is 3. So I want this potential here to be less than 3. That means the potential difference here should decrease. And if the potential difference here is to decrease, the potential difference here should increase. How do I increase PD across this? It is by increasing the resistance there, because this is a light-dependent resistor. The resistance there will only increase if the light intensity decreases. So let's think about it very carefully. When the light intensity of the LDR is increased, its resistance, is decreased, its resistance is increased, which means the PD across the LDR goes above 3. And if the total is 6 volts, if it goes above 3, then the PD across this one goes below 3. Therefore, the difference between them will be a positive, and therefore the voltmeter will give a positive reading. Remember, the voltmeter gives a difference in the potential between 2 points. So the most appropriate answer is going to be C. Reduce the intensity of light instead on the LDR. This one is going to increase the resistance of the LDR, which is going to increase the PD across the LDR, which means the PD across the thermistor is going to decrease. Therefore, the difference in these 2 points is going to be positive. When you decrease the temperature of the thermistor, what does that do? Decreasing the temperature of the thermistor instead increases resistance, which means the PD across Y is supposed to be above 3. So it will give us a negative value because this is fixed. So we have instead to decrease the light intensity. A nichrome wire has a resistance of 15 ohms and a diameter of 3 millimeters. The number density of the free electrons in nichrome is 9.0 times 10 power 23 per meter cubed. A PD of 6 volts is applied between the ends of the wire. What is the average drift speed of the free electrons? Average drift speed of the free electrons. So we know that current is equal to never, or current is equal to never. So the drift speed is going to be the current, which current is, where is the current? We have the resistance and we have the PD. So the current is going to be 6 divided by the resistance, which is 15. So 6 divided by 15. The current is going to be equal to 0.4 amperes. So the current is 0.4 amperes divided by, I'm making V the subject. N is 9.0 times 10 power 28. Then charge of an electron is 1.6 times 10 power negative 19. Divided by cross-sectional area, they gave us the diameter. Area is equal to pi d squared over 4. So the 4 goes up, so we shall say times 4. In the denominator we have pi, then diameter is 3 times 10 power negative 3, and that is squared. I can begin by solving the numerator, the denominator, which is 9 exponent 28 times 1.6 exponent negative 19 times pi into brackets 3 exponent negative 3, and this is squared. So that is the denominator. Then I'll say open brackets 0.4 times 4 divided by the answer, which is giving me 3.9 times 10 power negative 6. So this is 3.9 times 10 power negative 6 meters per second, which makes the answer to be B. The diagrams show two different circuits. The cells in each circuit have the same e.m.f and negligible internal resistance. The three resistors each have the same resistance R. In the circuit on the left, the power dissipated in the resistor is P, so power here is P. What is total power dissipated in the resistor on the right? So the power here is P, but we know that power is equal to V squared over R. So P is V squared over R. The power this side, I'll call it P2. Let me call it P2, which will be equal to V squared divided by total resistance, which is going to be twice R. Because these are now in series. The total PD is V because it divides, but then the resistance is R plus R. So what is the comparison between the two, this equation and this one here? So you notice that the second equation, P2 is equal to a half of the first, so it is a half of P, which makes our second power to be P over 2, which makes the answer to be B. The potential difference across a filament lamp is increased. Which statement is correct? What do we know about a filament lamp? If we remember the IV characteristic of a filament lamp, a graph of current against PD, the IV characteristic of a filament lamp, so that is I against V. If you remember very well, the curve was symmetrical about the x-axis, that initially for small voltage, the I is directly proportional to voltage and R is constant. But as PD increases, a point reaches where the temperature of the filament increases. And when the temperature of the filament increases, of course, the resistance also increases, because resistance is directly proportional to temperature. That's why we see with the time, as the PD increases, the current remains almost constant. So which statement is correct? The resistance of a filament lamp decreases because the temperature decreases. That's not true. The resistance of the filament lamp decreases because the temperature increases. The resistance is directly proportional to temperature. That is true. But the resistance, but this one is showing an inverse relation. The resistance of the filament lamp increases. We know that that one is true because the temperature decreases. This part is not true. The resistance of the lamp increases, which is true because the temperature increases. So the answer is going to be D. A metal wire has resistance R. The wire is stretched so that its diameter decreases to, it is 2, not by. Diameter decreases to 94.0% of the original diameter. The volume of the wire is unchanged. What is the resistance of the stretched wire? Resistance of the stretched wire. Okay, let's try to solve this. So we are going to think about resistance in terms of rho L. So we know that resistance is equal to rho L over cross-sectional area. But with they've given us in terms of diameter, so I have to remove the cross-sectional area. So this becomes 4 times rho L over pi d squared. I've removed the area because area is pi d squared over 4, where the 4 has gone up. But they say the volume remains the same. What is the relationship between the volume and area and length? So we also know that volume is equal to pi d squared over 4, which is cross-section area, then times the length of the conductor. That is volume. So let's first find the volume here. So for the first wire, let the volume be that one. For the first wire, let the volume be that one. So sorry, before stretching, let the volume be that one. Then after stretching, the volume is going to be pi. Where there is diameter, the diameter decreases to 94.0%. So that means the new diameter is going to be 0.94 of the original diameter. This is squared. Divide this by 4 to give us the new, then times the new length L, I'll call it L2. Remember, the volume remains unchanged. The volume remains unchanged. So I can combine these two equations. Let me change the color to combine the two equations. If I combine the two equations, I'm just going to equate them to find L2. So you notice that because volume is the same, so I have that pi into 0.94 d squared over 4 times L2 is equal to pi d squared L over 4. So 4 cancels, pi cancels. When I open the bracket, of course, it means L2 is going to be equal to, I'm making L to the subject, so d squared has cancelled, but 0.94 is also squared because the whole bracket here is squared. So I remain with 1 over 0.94 squared, then times L, the original length. So now that I know L, I go back to the expression resistance is equal to rho L over A to find, or 4 rho L over pi d squared to find the new resistance. So resistance R2 is going to be 4. Resistivity has remained the same. This time the length has changed. The length is 1 over 0.94 squared L divided by pi times d squared. Remember, 4 rho L over pi d squared is the original resistance R. So I just simplify this. Remember, the diameter here for the new wire is not d, it is 0.94 d. So I have to change this here. I'm substituting, so here it is supposed to be where there is diameter in this expression, because the diameter goes to 94%, so this is 0.94 d, and this is squared. So I factor out things, or I simplify things. I have 4 rho L over pi times d squared into brackets. I have 1 over, this one goes 0.94 going into the denominator. The d squared has been moved out, but remember this one is also squared, so it becomes 0.94 raised to power 4. The power, because it's 1 over 0.94 squared, again divide by 0.94 squared. But remember this part here alone, this part alone here is R. So it means R2 is going to be R times 1 over 0.94 raised to power 4. Let's check with our calculator and see what we get. 1 divided by 0.94 raised to power, where is the power? I can't see the power in this calculator. I don't know how to use this very well. But anyway, I can square it twice. There's no problem. So that one squared, I will square it twice because I don't know how to use power here. But I think I can. Okay, I don't know how to use power here. Let me just open the bracket. I say 0.94. I square it the first time and I square it the second time. There's no problem with that. Okay, 0.94 squared for the first time Again, I square the answer. That is what I have. Then I say 1 divided by the answer. That's 1.28. So this is going to give us 1.28 of R, which makes our answer to be D. The diagram shows a cell of e.m.f. 3 volts and internal resistance 4.7 ohms connected across a lamp. The lamp has a resistance of 9.3 ohms. What is the power dissipated by the internal resistance of the cell? So power here in the internal resistance is going to be I squared times small r. So we need to find the current only. So we know that current is equal to e.m.f, which is 3, divided by total resistance, which is 4.7 plus 9.3. So we have 3 divided by 4.7 plus 9.3. That gives us 0.21. So this is 0.21 amperes. I hope I added it very well. 4.7 plus 9.3. I think that is approximately 14. Okay, so 3 divided by 14. That is the current. So the power is going to be equal to I squared, which is 0.21 squared, times R, which R is 4.7. So the answer there, which is going to be squared times 4.7. And this is giving us 0.22. So power is going to be 0.22 watts, making the answer to be A. A circuit consists of a battery, a high resistance voltmeter, and 4 fixed resistors as shown in the figure there. The battery has an e.m.f. of 15 volts and negligible internal resistance. What is the reading of the voltmeter? What is the reading of the voltmeter? Okay, so to begin with, the PD across, total PD across these two is the same as total PD across the lower combination there. And we notice that total resistance, I can just find the current. So current is equal to the e.m.f. over total resistance. These two are in parallel, in series, giving us a total of 30. These ones are in series, also giving us a total of 15. So we get the product over the sum. But anyway, you will notice that the current in this part here, in the lower part, is going to be twice the current in the upper part, because the total resistance up there is twice total resistance down here. But anyway, this is going to be 15 divided by total resistance, which is 30. 30 times 15 divided by 30 plus 15. So this is giving us 30 times 15 divided by 45, which is giving us 10. So the total current there is going to be 1.5 amperes. I don't know whether that current is necessary, but anyway, it is fine. So what is the reading on the voltmeter? So to be able to find the reading of the voltmeter, let's just easily take a small part, or we can even find the PD across 1, but that is not necessary. We know that if the current here is I, because the total resistance here is 30 ohms, the current here is going to be twice I, because the resistance here is half. and current is inversely proportional to the resistance. Therefore, the PD across 20 ohms, PD across 24 ohms is going to be 24 times I. Then the PD across 6 ohms is going to be 6 times 2I. So this is going to be 12I. And the reading of the voltmeter is going to be the difference between those two. So it means the PD across the reading of the voltmeter, which is the PD between those 2 points, is going to be 24 minus 12 into I. That is the PD between those two. But remember, we have said that the current in, if the current in 24 ohms is I, the current in 6 ohms is 2I. We can even find that current. After all, we know the PD as 15. I is going to be 15 divided by total resistance there, which is 30. This gives us 0.5 amperes. So the reading there is going to be 12 times 0.5, which gives us 6 volts. I hope that is fine. The current I is the e.m.f over 30 because the PD here. Why did I find even the total current anyway? It wasn't necessary. So the total current here was not necessary because I'm not even using it. So the current through 24 ohms is 15 over 30. That gave me that current. But now to find the PD across these 2 points, I get the PD across 24 and the PD across 6, and I subtract, which gives me 6 volts. So it means our answer is going to be 6 volts. A potential divider circuit is designed to detect the difference in temperature between two different places. The cell has e.m.f 220 millivolts and a negligible internal resistance. Initially, thermistor X and Y are at the same temperature and have the same resistance. That means now the PD is the 20 millivolts is divided equally, giving this one 10 and the other one 10 if they have the same resistance at the same temperature. X is then placed in a cold environment. That means the temperature here, temperature drops, which means the resistance increases. That means PD across X must increase, must be above 10. And if it does, it means PD across Y must decrease, it must be below 10. X is then placed in a cold environment and its resistance doubles. Y is placed in a warm environment and its resistance halves. What is the new reading on the voltmeter? Note that the voltmeter is supposed to give us the PD across Y. Its resistance halves, so that means the PD must by all means be less than 10. That means 15 and 5 and 16, those ones are ignored already, they are above 10. So we have to choose between 4 and 5. The resistance, the voltmeter reads 10 millivolts. X is then placed in a cold environment and its resistance doubles. So resistance of X is double, so we shall say resistance of Y is halved. So I will say this one is half of R because they initially had the same resistance, and this one is twice of R. Let's find the PD across Y. So a half or I'll just say 0.5 R divided by total resistance, which is going to be 2.5 R, then times 20 millivolts. So 0.5 divided by 2.5 times 20, that gives us 4. So it means the new reading here is going to be 4 millivolts. So our answer is going to be A. There is an electric circuit, electric current in a copper wire. Which statement describing the average drift speed of the charge carriers in the wire is correct? Number 1, it is nearly 3 times 10 power 8 meters per second. Average drift speed of the charge carriers in the wire. It is proportional to the cross-sectional area of the wire. I is equal to never. So V is equal to I divided by NE times A. When you say it is proportional to the cross-sectional area, it is inversely proportional. It is proportional to the length of the wire. When the length, resistance is directly proportional to length, and resistance is inversely proportional to the current. So if resistance is directly proportional to length and is inversely proportional to the current, so they are saying it is proportional to the length. No, that is not true. It is instead inversely proportional. It is proportional to the magnitude of the current. That when we sit directly here, V is equal to I over that. So the answer is most likely going to be D. A battery with a constant internal resistance is connected to a resistor of resistance 250 ohms as shown in the figure there. The current in the resistor is 40 milliamperes for a time of 60 seconds. During this time, 6 joules of energy is dissipated by the internal resistance. What is the energy supplied by the external resistor to the external resistor during the 60 seconds, and the e.m.f, the electromotive force of the battery? Okay. So the current in the circuit is 40. So it is the same current here. It is the same current there. So first of all, during this time, 6 joules of energy is dissipated by the internal resistance. Energy is equal to power times time, which is equal to I squared R times T. So 6 joules is dissipated. So the current is 40 times 10 power negative 3, and this should be squared, times the internal resistance, which I'll call it small r, in a time of 60 seconds. So what is R? I'll just press my calculator. R is going to be 60. 6 divided by 60 divide by 40 exponent negative 3, but this is squared. So small r is 62.5 ohms. Okay, what is the energy supplied to the external resistor during the 60 seconds? And the electromotive force. Energy supplied to the external resistor, let's also find out energy. Energy is going to be, because we have the current, so it is going to be the current, which is 40 times 10 power negative 3. This is squared. The external resistance is 250. Then times the time, which is 60 seconds. Energy supplied is 40 exponent negative 3, that should be squared, times 250 times 60. So that is 24 joules. So we eliminate N and B. So the energy is 24 joules. So the question, the most important part is that the e.m.f, or the electromotive force. Okay, so to find the e.m.f, there are several ways. Let me see which one is easier. Now I know I can find the PD across this one and the internal, so that is very easy. e.m.f is equal to the PD across the external resistance plus the PD across the internal resistance. So this would be current into the big resistance plus the internal resistance. So the e.m.f is going to be the current, which is the current is 40 times 10 power negative 3 into The big resistance is 250. The internal resistance is 62.5. So this is 250 plus 62.5, then times 40 exponent -3. So that gives us 12.5. So the answer here is 12.5 volts, which makes the answer to be D. Which component has the IV graph shown? Of course, this is a filament lamp without even any station. That is a filament lamp, because we see as PD increases, there comes a point when the change in current is very small, simply because the temperature increases with the time, which means the resistance increases. And if resistance increases, the change in the current decreases. Two wires P and Q have the same resistance. Wire Q is made of material that has twice the resistivity of the material used to make wire P. The diameter of wire Q is twice the diameter of wire P. What is the ratio length of wire P over length of wire Q? Two wires P and Q have the same resistance. We know the resistance, I'll use the upper part. Resistance is equal to rho L over cross-sectional area, which is 4 rho L over pi d squared. Okay, so we are going to come up with three equations. Resistance of wire P is going to be 4. Wire Q is made of a material that has twice the resistivity of the material used to make wire P. So for wire P it is rho, for wire Q is going to be twice rho. So this is going to be rho. The diameter is twice. So it is going to be rho length of wire P divided by pi. The diameter of wire Q is twice the diameter of wire P. So for wire P is D, so this will be D squared. For wire Q it is going to be twice D. So another equation for P, for Q, resistance of P is going to be 4. The resistivity for Q is twice, so this is going to be twice rho. The length I will call it LQ divided by pi. The diameter is also twice, so this will be twice D, and this should be squared. So we have those two equations. Remember, the resistance is the same, so I just equate the two. So I will say 4 rho L of P divided by pi d squared for P should be equal to, that will be 4 times twice rho L of Q divided by pi times 4 d squared. So some of these quantities cross out, 4 cancels, pi cancels, d squared cancels, rho cancels. So I remain with L of P is equal to twice L of Q divided by 4. So it means when I simplify this, it becomes a half. So L of P divided by L of Q is equal to a half, making the answer to be C. A voltmeter reads 9 volts when it is connected across the terminals of a battery. Okay, it reads 9 volts. When a resistor of resistance 11, so here it is giving the e.m.f. So the e.m.f is 9 volts. e.m.f is 9 volts. When a resistor of resistance 11 ohms is connected in parallel with a battery, the voltmeter reading changes to 8.8. So the terminal PDVT is, I'll quote VT, is going to be 8.8 volts. So we can tell the lost volts. The lost volts is going to be 9 minus 8.8, which gives us 0.2 volts. That is lost within the battery. What is the internal resistance of the battery? That is very easy. We know that lost volts is going to be equal to the current. Lost volts is equal to the current times the internal resistance. Let's check if we have the current. No, but we can still find the current. Okay, we can still find the current. Since I know the PD across this one and as being 8 volts, so I can tell the current here. The current here, or the current in the battery, is going to be equal to the PD, which is 8.8 divided by the resistance, which is 11. So it means the lost volts, which is 0.2, is equal to the current, which is 8.8 divided by 11 times the internal resistance, small r. So that is 0.2 times 11 divided by 8.8, which gives us 0.25. So small resistance R is 0.25 ohms, which makes our answer to be B. So note how I have played around with this. When there is no any other thing in the external circuit, the reading of the voltmeter is the e.m.f. That's number one. Number two, when there is something connected in the circuit, then the reading of the voltmeter is the terminal PD, which is the PD given to the external circuit, which is 8.8 volts. That means the lost volts, what is lost within the battery is the difference, which gives us 0.2 volts. And the lost volts in the battery is the current through the battery times the internal resistance. So we had to find the current because we know the current is the same through the battery and the fixed resistance of 11 ohms. Then we used Ohm's law where I is equal to V divided by R. That gave us 8.8 over 11. So I substituted for the current and we were able to find the internal resistance as 0.25. Each of Kirchhoff's laws is linked to the conservation of a physical quantum. Of course, that is very easy. The first law, sum of currents into a junction is equal to sum of currents out of a junction. That is conservation of charge because current is the rate of flow of charge. The second one, sum of EMFs is equal to the sum of PDs around a closed loop. EMFs and PDs, that is energy per unit charge, although for EMF it is energy from chemical to electrical, and for PD it is energy from electrical to thermal. So that means for Kirchhoff's law it is charge, the first law it is charge, the second law it is energy, so the answer is going to be C. 3 batteries and 3 identical resistors are connected in a circuit PQR as shown in the figure here. It looks complex, but it might be very easy. The batteries have negligible internal resistance. What is the potential difference between points P and Q? Okay. First of all, let's find the net effective EMF. We're going to find the net effective EMF. So to find the net effective EMF, we look at the cells, or I can even put a loop in there. Let me put a loop which is anti-clockwise. So EMF total is going to be moving around the loop. We have 9.6 minus 8.4 plus 6.3, which gives us, I think that is 7.5 without wasting time. Let me check. 9.6 minus 8.4 plus 6.3. That is 7.5 volts. That is the net EMF. Net EMF, so this is net EMF. Because the batteries are identical, this is the resultant EMF in the circuit, and the batteries are actually identical. So it means the PD, or the effective EMF, is going to be shared equally. Since the resistors are identical, it is going to be shared equally. The 7.5 is going to be shared equally among the 3 resistors, which means this one will take 2.5, this one will take 2.5, and this one will take 2.5 volts. The 7.5 has been shared equally. So the question is, what is the potential difference between points P and Q? Potential difference between points P and Q. So assuming you put a voltmeter, say, at this point, let's put a voltmeter across those 2 points. No, P and Q is the other side, so I have to change this. So let's put a voltmeter here. So remember, this is taking 2.5 and the EMF is 9.5 volts. So the reading of the voltmeter must be the PD outside the cell, outside this battery here. Therefore, the reading of the voltmeter V is going to be the terminal PD the other side, which is going to be 9.6 minus the lost volts, which is going to be 2.5. And this gives us 9.6 minus 2.5. That gives us 7.1. Which means our answer here is going to be C. Not exactly how I arrived at this. This is quite abstract, of course, I know that. But I want you to note, first of all, I found the net EMF in the circuit. By using Kirchhoff's second law, I drew in a loop and I tried to move around the loop, which meant 9.6 was positive, 8.4 was negative, 6.3 was positive when I move around the loop. So this is the net EMF in the circuit. Because the cells, the resistors are identical, then this EMF is going to be divided equally among these three resistors. That's why I divided 7.5 by 3. So each was taking 2.5. And if each takes 2.5, then I realized you noted that if I put a voltmeter between P and Q to find the potential difference between P and Q, then the voltmeter should give me a reading of the PD outside that combination, which meant it would give me a 9.6 minus 2.5. That is the balance from 9.6 minus 2.5 must be the PD outside that side or outside that branch. That's why I arrived at 7.1 by subtracting those values. Okay. A cell E of EMF 2 volts and negligible internal resistance is connected to a uniform resistance wire of resistance 10 ohms and 1 meter. Okay. Z is a connection that may be made at any position along the resistance wire. A galvanometer is connected between Z and a point Q. A new source of EMF of approximately 80 millivolts is connected between points P and Q. So here we have a source of approximately 8 millivolts. Okay, the EMF of the new source is determined by changing the position of Z until the reading on the galvanometer is 0. So to find about 8 millivolts, we have to change the position of Z until the galvanometer reading is 0, which change to the circuit allows a much more precise value of the EMF of the new source to be obtained. Number 1, add a resistor of resistance 0.1 ohm in series with the cell E. 0.1 ohm in series with a cell E. Okay, 0.1 in series. What was the resistance? The resistance of the is connected on a uniform. Okay, the resistance was 10 ohms. So if we add a resistance in series, 1 ohm here, 0.1 ohm there, it means the PD across these 2 points is going to be resistance. Okay, the resistance of the wire is going to be 10 ohms divided by total resistance, which will be 10. No, not 10. It will be 0.1. How should I simplify this? Okay. So if this is 2 volts, this is approximately 2000 millivolts. That is approximately 2000 millivolts. Okay, so we want a more measurable, because the question is which change to the circuit allows a much more precise value for the EMF of the new source. We want a much more precise value for the EMF of the new source. We have options: add a resistor of resistance 0.1 ohms in series with the cell E. So if we put here 0.1 ohms, does it help us in any way to find this? My answer is going to be no. Suppose we put there a resistance of 1000 ohms in series with the cell E. Because 0.1 is very small, it has very less effect, but let's say if it is 1000 ohms. In that case, remember the wire is 10 ohms. So it means if we try to find the PD, then it means this will be 10 over 10 plus 1000 because they are in series. Then times the EMF, which is 2000 millivolts, remember. This would give us 10 divided by 1010 times 2000. That will give us around 19.8 millivolts. So this will give us 19.8 millivolts as actually the PD across this wire here, 19.8 millivolts. So this value is relatively big that it can help us to easily measure the PD across Z. But think of a situation where I use 0.1 to give us the PD across this wire would be 10 divided by, remember this is 0.1 plus 10, that is 10.1, then times 2, then times 2000. So this is going to give us the PD across the wire is almost 2000. The PD across the wire is almost 2000, which is almost the same as the EMF of cell E. So this would be, let's check, 10 divided by 10.1 times 2000. So that is actually giving us approximately it's almost 2000 millivolts, and yet they said the EMF across between of the cell placed at PQ is going to be approximately 80 millivolts. That means 0.1 will not really work. So you can go on checking 10 ohms, you can check 800 ohms, maybe you can check 10. For 10 ohms, the PD across the wire would be, the wire has 10 ohm resistance over 20 because the sum will be 10 plus 10, then times 2000. So that is a half of 2000, that is 1000. That will be also too big PD across that wire. So you can also check 800, but the most appropriate is going to be B. For a current carrying wire, the current can be calculated using the equation I is equal to AN VQ. Okay. What is the meaning of N? Remember, N is number density of charge carriers, number of free electrons per unit volume. So we just look for that. Number of charge carriers per unit volume, the answer is D. The number of free electrons passing a point in a wire is in 24 hours is this. So they have given us number of electrons and time. What is the average current in the wire? So remember, current is the rate of flow of charge carriers. So it is charge over time. The number of electrons, and charge is number of electrons times the charge of each electron, then divided by time. So this will be 6.0 times 10 power 23, 1.6 times 10 power negative 19, divided by time, which is 24 times 3600. So we have 6 exponent 23 times 1.6 exponent negative 19 divided by 24 times 3600. So that gives us approximately 1.1. So the answer is going to be B, which is 1.1 amperes. In the circuit shown, lamp P is rated 250 volts, 50 watts, and lamp Q is rated 250 volts, 200 watts. The two lamps are connected in series to a 250 volt power supply. Assume that the resistance of each lamp remains constant. Which statement most accurately describes what happens when the switch is closed? Remember, they have the same okay, let's check. Assume that the resistance of each lamp remains constant. Let's first check the resistance of each lamp. So for P, resistance for P is going to be using the formula, resistance is power is equal to V squared over R. So resistance is going to be the power. For P, it is going to be 50. No, it is going to be 250 squared divided by the power, which is 50. Let me make this clear. So this is going to be 250. I'm making R the subject, so 250 squared over 50. And the resistance for Q is equal to 250 squared over 200. We can check. 250 squared divided by 50. That is 1250. And then 250 squared divided by 200. That is 312.5. That is 312.5. I think there is a relationship between these two values. Let me try to divide them. I'm going to divide resistance of P divided by resistance of Q. So I have 1250 divided by the answer, and it is 4. So it's like resistance of P is equal to 4 times resistance of Q. Okay. So which statement most accurately describes what happens when the switch is closed? Number 1, lamp P emits 4 times as much power as lamp Q. Let's check the power emitted in each of these lamps. The power emitted in each of these lamps is going to be equal to probably I times V. Remember the resistance, of course, you also note that V is equal to I times R. The current through them is the same, so this one is the same. I'll put it in brackets because it's the same. Resistance of P is 4 times resistance of Q, meaning PD across P should be 4 times PD across Q. What does that mean? Because power is equal to I times V, it also means the power of P is going to be 4 times the power of Q. So power of P must also be 4 times the power of Q, because from power is equal to IV and I is the same, and resistance V is directly proportional to R for a constant current. If R for P is 4 times R for Q, then V for P is 4 times V for Q. And therefore, if I is constant, power for P is 4 times power for Q. So the answer is going to be A. A piece of wire has length 0.8 meters and diameter 5.0 meters. 5.0 times 10 power 4 meters. The IV characteristic of the wire is shown here. So that is the IV characteristic. What is the resistivity of the metal from which the wire is made? Let's first find the resistances. So resistance is going to be equal to, I'll just take full values, V over I. That is 10 divided by 5, which I think is 2 ohms. That is the resistance. So resistance is equal to rho L over cross-sectional area. And we know that area is pi d squared, so this is going to be 4 rho L over pi d squared. So we want the resistivity, so I'm just going to substitute resistance is 2 equaling 4 times resistivity. The length is 0.8 divided by pi. The diameter is 5 times 10 power negative 4, and this is squared. I'll just press my calculator. 2 times pi into brackets 5 exponent negative 4 squared divided by 4 times 0.8. So we are getting 4.9 times 10 power negative 7. I hope that is correct. 4.9 times 10 power negative 7 ohm meters. So the answer is going to be C. 10 cells, each of e.m.f 1.5, are connected together as shown. What is the combined e.m.f between the terminals X and Y? So I'll just put Kirchhoff, I'll put a loop around there, which is anti-clockwise. So this one is the other way around, its e.m.f is negative. The rest are the other way around. So this is 1.5 plus 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 1.5 minus 1.5. In other words, I will say 1.5 times 1, 2, 3, 4, 5, 6, 7, 8, 9 times 9, then minus one cell which has 1.5. And I think that is 12. 1.5 times 9 minus 1.5, which is 12. So our answer is going to be 12. So this is equal to 12 volts. A cell of e.m.f, E, and internal resistance R is connected to a variable resistor as shown here. The resistance of the variable resistor is gradually increased from R to 3R. So resistance is increased from R to 3R. Which graph shows the variation of the potential difference V across the internal resistance and PdV across the variable resistance resistor? Okay. So first of all, the e.m.f E is going to be the capital value of V plus the small value of V, because it is terminal PD plus internal resistance. When R is equal to capital R, when capital R is equal to small r, it means the e.m.f is going to be shared equally because they're in series. So it means E would be equal to 0.5 E plus 0.5 E. It is going to be shared equally when they are equal. It means PD across capital V is equal to small v when they which means PD capital V is 0.5 E and small v 0.5 when R is equal to capital R. So that means our graph starts from 0.5 E, and I think all graphs are starting from there. 0.5 E. Okay, that one can't help us to eliminate anything. Now what happens when R, capital R, is 3R? When, because the resistance of the variable resistor is gradually increased from small r to R. So when capital R is equal to 3R, what happens to the PD? Because the resistance of V of the variable resistor has increased 3 times. It also means that capital V should be equal to 3 times small v. Capital V will be 3 times small v. That means as R, as the resistance of the variable resistor increases, it means the PD across the variable resistor is going to actually be increasing. I mean, yes, it is going to be increasing. But of course, as capital V increases, it means small v must be decreasing. Therefore, the graph should be decreasing. Small v must be decreasing as capital V is increasing. So here it is showing the reverse. It is showing capital V decreases as small v decreases. That is not true. This is showing capital V decreases. This is showing capital V increases and also small v increases. That is not possible. So our answer is going to be A. When the terminal PD increases, then the velocity volts must decrease. Therefore, our graph is going to be A. When the terminal PD, which is capital V, increases, the velocity volts, which is small v, must decrease because the sum must remain the EMF. Each of Kirchhoff's two laws presumes that some quantity is conserved. Remember, we have said first law, charge, second law, energy. Which law states Kirchhoff's first law and the names and the quantity that is conserved? Algebraic sum of current into a junction is zero. That is the first law. That is conservation of charge. That is true. Algebraic sum is zero. Energy, that is not true. EMF, that is energy. EMF in the loop is equal to the algebraic sum of the product of current and the resistance around the loop. Okay? Conservation of energy. EMF in a loop is equal to the algebraic sum. No, that is, okay, the algebraic sum of the product of current and resistance around the loop. The algebraic sum. EMF in a loop is equal to the algebraic sum no, the word algebraic makes this not make any good sense because the algebraic sum of the EMFs and the potential drops must be zero. A cell has an EMF of 8 volts and negligible internal resistance. The cell forms part of a circuit as shown in the figure down here. The reading V1 is 4 volts. The reading V2 is also 4 volts. Okay. What is the resistance of resistor R? So if the reading here is 4 volts, we can find the current. We can find the current there because we can tell the total resistance. 4 ohms plus 4 ohms gives us a total of 2 ohms because they're in parallel. So resistance in parallel is going to be 4 times 4 divided by 4 plus 4, which is equal to 2 ohms. We can find total current there, which is going to be the total current entering or leaving that junction. Current is going to be equal to the PD, which is 4, divided by the resistance, which is 2. That gives us 2 amperes. So it is the current there. V1 is also 4. So we can find the resistance. Resistance from Ohm's law is V over I, which will be 4 divided by 2. And precisely this gives us 2 ohms. Very simple. So our answer is going to be B. In the circuit shown, the cells have negligible internal resistance and the reading on the galvanometer is 0. Okay, this is quite technical, but it's very simple and sweet. What is the value of resistor R? Okay, so I want you to notice that the reading of the galvanometer is 0. That means the potential here is the same as the potential here. But already the potential here and here are the same because these two are directly linked. So what does that mean? If the potentials here are the same, it means the PD across 9 ohms must be the same as the PD across PD across 6 ohms. Let's use the potential divider formula to get the PD across 9 ohms. Because remember, the 4 volts must be divided among these. It is the same PD because these two are in series. So it means using the potential divider formula, PD across say 9 ohms is going to be the resistance of 9 over total resistance in that branch, which is 9 plus 3 times the voltage supply, which is 4, to get what PD is across 9. So this is going to be 9 divided by 12 times 4, that is 3 volts. So the PD across 9 ohms is 3 volts, not 3 ohms. So that is 3 volts. So we now know that this is 3 volts, but is in parallel with this one, so this is also going to have 3 volts. The PD is going to be the same. And if that is 3 volts, yet the total PD, the PD across this combination here is 4 volts. So this is 3 volts, that means this is going to be 1 volt. But if this is 3 volts, again the battery supply here is 9 volts. So we can predict the PD here is going to be 9 minus 3, which is equal to 6 volts. So the PD across here is going to be 6 volts. Alternatively, you can also find it by saying, okay, using 9 volts, 6 divided by total resistance, which is going to be 6 plus the resistance R should give us, or times 9 volts should give us 3. I've just used the potential divider formula. We know that the PD across 6 ohms is now 3 volts. But I should be able to get this same 3 volts when I use 9 volts as the EMF this side. Therefore, 6 over total resistance, which is 6 plus R, divided by, times the voltage supply, which is 9, should be able to give me 3. So I just solve this equation. So I have 6 plus R is equal to 6 times 9 divided by 3. So I have 6 times 9 divided by 3. Then I subtract. I will say minus 6, which gives us 12. So R is going to be 12 ohms. Therefore, it means our answer here is going to be C. Note how I arrived at this. I used the upper loop to find the PD across 9. I used the upper branch to find the PD across 9 ohms, which was 3. But now 9 ohms is in parallel with the 6 ohms if the galvanometer gives no reading. So it means the PD across 6 ohms is 3 volts. Therefore, because the EMF down there is 9 volts, I should be able to get 3 volts across 6 if I use the lower branch. Alternatively, I could arrive at the same thing by saying, okay, the resistance here is not known, but the PD across there is 6 volts because it is 9 minus 3. So I can say R over total resistance, which is 6 plus R, then times the voltage, the EMF of the cell there, which is 9, should also give me 6. Because the PD across here is 9 minus 3, which is 6. So we solve this. 9R is equal to 36 plus 6R. So again solve this. 3R is equal to 36, which means R is going to be 12 ohms. A straight copper wire of diameter 0.42 times 10 power negative 3 meters has a number density of free electrons of 8.5 times 10 power 28 per meter cubed in a given time interval. A charge of 0.15 coulombs moves through the wire. What is the average displacement of the free electrons along the wire in the time interval? Okay, so we know that current is equal to never or N. Okay, never. We want the average displacement. So to find displacement, of course, we know that time is always the displacement divided by speed if the speed is constant. So we want S. So I'm going to remove V here and I bring in S and T. So current is going to be NE where there is V. I'm going to put S divided by T, that is displacement over time, times area. So let's substitute. S is going to be the current. What is the current? The current is charge. I is charge over T. So this is going to give us the charge, which is 0.15. That is the current. Then over the time, we don't have time here, okay. Current is that over time. Then I will divide this by, I'm making S the subject, remember. I will divide this by, of course I've already multiplied by T because there's a T in the denominator. Current alone is charge over time. So this is going to be divided by N. What is N? N is 8.5 times 10 power 28. Then times charge of one electron, 1.6 times 10 power negative 19 times cross-sectional area. They gave us diameter. The situation is very long. Let me repeat this. I have to simplify this further. I'm going to remove the area so that I put diameter directly. So multiplying T the other side, we have IT is equal to N charge times area, which is pi d squared over 4, then times S. I times T is charge. So charge is equal to N E pi d squared. I'm taking the 4 the other side, then times S. So S is going to be 4 times the charge, which is 0.15, divided by, I'm making S the subject, remember, N, which is 8.5 times 10 power 28. E is 1.6 times 10 power negative 19 times pi, then times diameter, which is 0.42 times 10 power negative 3, and this is squared. So let's press our calculator. I'll begin by simplifying the denominator. 8.5 exponent 28 times 1.6 exponent negative 19 times pi times 0.42 exponent negative 3. So I'll say the numerator, which is 4 times 0.15, divided by the answer. So I am getting 7.9 times 10 power negative 5, which is approximately 8.0. So S is 8.0 times 10 power negative 5 in meters. This makes our answer to be C. What is the definition of potential difference across a component? We know that V is the work done per unit charge. In other words, the energy transferred from electrical to thermal energy per unit charge. So let's check. Electrical power supplied to the component, not at all. The energy transferred to the component per unit charge. So this is going to be B. Energy transferred from electrical to thermal per unit charge in the component. The graph shows the IV characteristic of a semiconductor diode. Okay. Which statement can be deduced from the graph? Okay. Above a certain positive voltage potential difference, the diode obeys Ohm's law. Let's check. Not at all. It is not a straight line through the origin. Current is directly proportional to potential difference when the current in the diode is in one direction. It is not a straight line. So this is also not true. The diode has zero resistance when the current in the diode is in one direction. Zero resistance. Here, when you see that there's almost no current for negative values, it means the resistance is equal to infinity. So it means that is not true. The resistance of the diode depends upon the potential difference across it. And I think this is very true. Resistance is equal to V over I. So the resistance of the diode will depend upon the potential difference across it. When the PD reaches a certain value, then the resistance decreases, and then the current flowing increases. So the answer is going to be D. A wire has a resistance of 30 ohms. The second wire is made from the same material, has the same mass, and is 3 times as long as the first wire. What is the resistance of the second wire? Okay, so first of all, we know that resistance is equal to rho L over cross-sectional area. What is the relationship between area and mass? We know that density is mass over volume. I'll use D for density because we have rho there. So density is mass over volume, meaning mass is equal to the density times volume. But remember, volume is cross-sectional area times length. So this is going to be density times cross-sectional area times length. So if I make area the subject and I remove area, it means the area is equal to mass divided by the density times the length. Okay. So this resistance is going to be rho. Is going to be rho. Where there is area, I'm going to put mass over density times length. So density times length goes up. So this will be equal to rho L times the reciprocal, which is density times L over m. In other words, it is rho L squared D over m. Okay. So now let's come up with equations. Let the first wire have resistance R, which is rho L squared D over m. Then the second wire is made from the same material, meaning rho is the same, has the same mass, m is going to be the same, and is 3 times long. L is going to be 3 times L. What is the resistance? So this is the first wire. So the second wire is going to be resistivity is the same, length is 3 times. So we shall have 3L squared, and D is the density because it is from the same material. So D is density is the same, and the mass is also the same. When I simplify this, I just simplify the 3 squared, it becomes 9, so it will be 9 times rho L squared D divided by M. Note that rho L squared D is the first resistance, so it means R2 is going to be 9 times R1. So when we substitute, this will be 9 times R1, which is going to be 30. 9 times 30, that is 270. So this is 270 ohms, making the answer to be D. Note this mathematics here. A cell has internal resistance R and e.m.f. E. The cell is connected in series with an ammeter and a variable resistor of resistance R. Okay, so we see the diagram here. When R is 10 ohms, the ammeter reads 0.3 amperes. When R is 5 ohms, the ammeter reads 0.4 amperes. What is the EMF? The value of EMF, I. So note that the current is always going to be the same. So we are going to come up with a few equations here. The EMF, remember, is equal to I into R plus small r. The EMF is not going to change here. So for the first case, EMF is equal to the current is 0.3 into R, capital R is 10 plus small r, which is not known. Then for the second case, the EMF is going to be equal to the current is 0.4, capital R is 5, small r remains r, it is constant. Then we now solve these two equations. Because I want E, I'll make small r the subject in one of these equations. For example, I can say, okay, from the first equation, I will say that E is equal to 3 plus 0.3 r, which means small r, or let me just combine them naturally. I will just solve r for for E again. Let me eliminate E by first of all finding small r. Equating the two equations, I will have that 3 plus 0.3 small r is equal to 0.5 times 0.4 times 5, I think that is 2. So this is going to be 2 plus 0.4 r. So collecting like terms, it means 0.1 r is going to be equal to 1. So it means r is 1 divided by 0.1, I think that is 10. So small r is going to be 10. I hope it is 10. Let me check again the algebra. 0.5, that is 2, 0.4 r, 0.3 times 10, that is 3. Okay, I hope small r is that. So let's now substitute in one of the equations for small r. So it means the e.m.f is going to be equal to, let's say, 0.4 into 5 plus 10. So that is 15 times 0.4, which is giving us 6 volts. So this is 6 volts. So the answer is going to be D. The sum of the currents entering a junction in an electrical circuit is always equal to the sum of the currents leaving the junction. Why is this? That is consequence of conservation of charge. That is very simple. Conservation of charge. In the circuit shown, the temperature remains constant. The temperature remains constant. In which circuit does the potential difference V increase with the increasing light intensity? So here, of course, A is wrong. They're saying in which circuit does the PD increase with the increasing light intensity? This is a thermistor, so this one does not contribute to anything, doesn't contribute to the answer. Okay, so because here we only have a thermistor and a fixed resistor, there is no effect because the thermistor depends on temperature, not light intensity. So let's look at the remaining ones. B, we want V to increase when light intensity increases. Here you see that when light intensity increases here, resistance decreases. And from V is equal to IR, it means V decreases. So this one will not be correct. We are now here. Light intensity increases. It is the same thing. Resistance decreases, which means V decreases. So this is not going to be correct. Let's look at this. Light intensity increases, here resistance decreases. Potential difference here across the light dependent resistor decreases because the resistance of the LDR is decreased, but V is measured from the thermistor. If it decreases here, and remember the e.m.f must be the PD across the thermistor plus the PD across the LDR. If it has decreased for the LDR, it must increase for the thermistor so that the e.m.f remains the sum of these two. So it means the answer is going to be D. When the light intensity increases, the PD across the LDR decreases, but the PD across the thermistor will therefore increase. So it means the answer is going to be D. Those are potential dividers. The diagram shows a metal block. The block has sides of length A, B, and C as shown, and its volume is V. Each charge carrier has a charge negative Q, and the number density of the charge carriers in the metal is N. It takes each charge carrier an average time of T to pass through the block. What is an expression for the current I? Remember, current I is equal to never So now we have to manipulate this. N should remain, E should change to Q. So this is going to be N, Q, the negative, I'm going to ignore it. Then drift speed V, they gave us, it takes charge carrier an average time T to pass through the block. Let's find the distance from this side to the other side. The distance is going to be B. So where there is V, V is going to be distance over time. So this is going to be D divided by T. Okay. So not D, it is B. It is B divided by T. So that is V. Then cross-sectional area, they have given us the volume is V, and we want volume to, we don't have A in that expression. Cross-sectional area is equal to, the cross-sectional area is going to be this one here. So it is going to be C times A, that is the cross-sectional area. And yet the volume is going to be cross-sectional area times another length, which is B. So volume is going to be cross-sectional area, which is CA times B. So CA alone is cross-sectional area. In other words, where there is area, I will put there volume divided by B. Yes, volume divided by B. Now I will substitute where there is area. I'm coming back here. Where there is area, I will put there volume divided by B. So this is capital V. So you will notice carefully that B has cancelled, and therefore the current remaining becomes N Q volume divided by T, which makes our answer to be precisely B. The circuit diagrams show two lamps X and Y, each connected to a cell. The current in lamp X is 0.5 amperes. Its resistance is 9 ohms. The current in lamp Y is 3 amperes. Its resistance is 1.2 ohms. What is the ratio? Power in lamp X over power in lamp Y. So we know that power is going to be equal to I squared times R. So I'll just find the ratio. So this ratio is going to be, for X, it is going to be 0.5 squared times 9.6 divided by, for Y, which is 3 squared times 1.2. So we press the calculator, 0.5 squared times 9.6 divided by 9 times 1.2. I just squared the 3, which gives us 0.2222 recurring. So this is 0.22 recurring. So the answer is going to be A. The intensity of light incident on a light-dependent resistor is increased. That means resistance decreases. The temperature of the thermistor is increased. It means the resistance decreases. In each case, the current in the component is maintained at a constant value. What happens to the potential difference across each component? So V is equal to I times R. R is decreasing. I is constant. It means V must also be decreasing. So in both cases, it is decreasing. When intensity of light increases, resistance of the LDR decreases. When the temperature of the thermistor increases, resistance decreases. If the current is the same from V is equal to IR, it means V decreases in both cases. An iron wire has length 80 meters and diameter 0.5 millimeters. The wire has resistance R. A second iron wire has length 2 meters and diameter 1 millimeter. What is the resistance of the second wire? They are both iron, so that means the resistivity is the same. Resistance is equal to rho L over cross-sectional area, which is 4 rho L over pi d squared. So rho is the same. Rho is the same. And if rho is the same, so for the first wire, the resistance is going to be 4 times resistivity The length is 8 divided by pi. I will not change the units of diameter because I'm not okay. You notice that the new value of diameter is okay. Maybe let me change, no problem. So this is going to be times this is 0.5 times 10 power negative 3, and this is squared. The second wire, the resistance is going to be 4 times rho. Its length is 2 meters divided by pi, and this is the diameter is going to be 1 times 10 power negative 3, and this is squared. So we simply combine these two to find the resistance of the second wire. I'll just divide them. I'm dividing R2 by R1. So I have 4 rho times 2 over pi into 1 times 10 power negative 3 squared, divide by, I get the reciprocal, pi into 0.5 times 10 power negative 3, and this is squared, divide by 4 rho times 8. So 4 rho cancels, pi cancels. This was 4 rho times 2, so I have by 2, 1 by 2, that is 4. I will just press my calculator. So I have 0.5 exponent negative 3 squared, divide by 1 exponent. Now in the denominator I have a 4 here. So it will be 4 times, so I'll say divide by 4 into brackets 1 exponent negative 3 squared. That is 1 over 16. 1 over 16, which is okay, 1 over 16. So it means R2 over R1 is equal to 1 over 16. That means R2 is R1 over 16. And R1 is just R. So the answer here is going to be A. A cell with a constant e.m.f is connected across a fixed resistor. Over time, the internal resistance of the cell increases. Which change occurs to the internal resistance of which change occurs as the internal resistance of the cell increases? Internal resistance increases, the current flowing through the circuit. The cell of constant e.m.f is connected across a fixed resistor. Let's try to sketch this here. So we have a cell with some internal resistance. It is connected across a fixed resistor. The internal resistance changes, so I'll put an arrow there. This is the cell. So this is fixed. So remember the EMF is equal to PD across R plus the lost volts, PD across small r. So remember, the internal resistance increases. If the internal resistance increases, it means the current flowing through the circuit decreases. The current flowing through the circuit decreases, which means the terminal PD is most likely going to decrease. So we are saying a decrease in the charge of each charge carrier, not at all. A decrease in potential difference measured across the cell. That will be the terminal PD here. So the answer is going to be B. Because if the current has decreased, if I decreases, terminal PDR is equal to I times capital R. I has decreased, means V across R decreases. The answer is B. There will be a decrease in the potential difference measured across the cell. That is the terminal PD. Kirchhoff's first and second laws are consequences of the conservation of different quantities. We know first law is charge, second law is energy. So first law is charge, second law is energy, so the answer is precisely A. A potentiometer circuit is used to determine the e.m.f, EX of a cell. The circuits include a second cell of known e.m.f E0, a negligible internal resistance, and a uniform resistance wire PQ of known length. EX is less than E0. EX is less than E0. Let's check the diagram. The movable connection J can be positioned anywhere along the length of the resistance wire. Which circuit is suitable for determining EX? We are determining EX. A potentiometer circuit is used to determine the e.m.f EX of a cell. The circuit includes a second cell of known e.m.f E0. But they are saying EX is less than E0. That means E0 is going to be the driver cell. Therefore, we can't connect the galvanometer, which is going to give us a 0 reading. We can't connect it to E0. Otherwise, we may never get balance if we put the galvanometer with E0. So let's check every circuit where the galvanometer is connected to E0 must be wrong, because that means we shall never get balance. So this one, yet since E0 is greater than EX, we can never get balance when the galvanometer is connected to E0. Therefore, this is wrong. I think it is the only one. So we have eliminated B. Secondly, to get balance, remember how we connected this in the laboratory. The positive terminal of the driver cell must be directly linked to the positive terminal of the cell whose e.m.f is known. So let's check that. So this one is showing positive is linked to negative. We shall never get balance. So this one is also wrong. This one is showing a negative to negative. We could get balance. This one is also showing negative to negative. So we have eliminated A. We are remaining with C and D. Okay. So let's now check. Remember I said when the galvanometer is connected to E0, we shall never get balance because E0 is greater than EX. That means this one is also wrong because you see the galvanometer is linked to E0. It means we shall never get balance because the e.m.f of E0 is greater than that of EX. Therefore, the most appropriate solution will be D. Note very carefully, balance cannot be achieved. We eliminated A because balance cannot be achieved if the cells are connected like this. Positive to negative, there will never be balance. Balance is only achieved if positive is connected to positive so that there is a possibility of cancellation. We ignored this because there is no way we can get balance when the galvanometer is connected to a cell of a higher e.m.f. It means the PD is not going is either going to be higher, but will never be less than, it will never be equal to EX. There will never be balance. We said this one is also wrong because the galvanometer is connected to E0, which E0 is greater than EX. Therefore, our answer is D. Two wires, X and Y, are made from the same metal. That means they have the same resistivity. The diameter of wire X, Y is twice that of wire X. X is D, Y is twice D. What is the ratio? Wire X, wire Y, and the battery are connected in series. That means the current is the same. What is the ratio average drift speed of free electrons in wire X over average drift speed of electrons in wire Y? Okay, so we know that drift speed V is equal to the current divided by the number of charge carriers, the charge of each carrier times the cross-sectional area A. They have given us diameter. We know that area is equal to pi d squared over 4. So drift speed is going to be 4I divided by n e times pi d squared. So we want drift speed of wire X, so that I'll quote Vx, over average drift speed of wire Y, I'll quote Vy. So this is going to be 4. The current is the same. N is going to be the same. E is the same times pi. Diameter for X is D. So I just say D squared. divide by, so I'll get the reciprocal. So n e pi diameter is twice for y, so this is twice d, and this is squared, divide by 4 times I. Some of these things are cancelling out. 4i cancels, n e pi cancels. So this gives us 4d squared divided by d squared, which gives us 4 over 1. And this precisely makes the answer to be D. A resistor has resistance R. When the potential difference across the resistor is V, the current in the resistor is I. The power dissipated in the resistor is P. Work W is done when charge Q flows through the resistor. What is not valid? A valid relationship between these variables. I is equal to P over V. I think that one is fine. P is IV. Q is W over V. That means PD is equal to work done per unit charge. That is correct. P is equal to I squared R. I think that is correct. This one is saying P is equal to V over R. That one is wrong. So this is wrong. It is supposed to be P equals to V squared over R. The answer is D. It is not valid. A fixed resistor and a filament lamp are connected in series to a power supply. The IV characteristic for the two lamps are shown. Okay, so these are the IV characteristics for the two lamps. So for the two components, for a fixed resistor, they are connected in series. It means the current is the same. I is the same because they're in series. The current in the fixed resistor is 0.34. It must be the same current in the filament lamp. So let's first look for 0.34. So the scale here is 0.1 divided by 5, which is 0.02. So 34 is here. So 34 is giving us a PD of 6. Then the current here should also be 0.3412. And it is giving us 4.2 volts. So this was 6 volts and 4.2 volts. Okay. What is the resistance of the filament lamp? So we now know the PD across the filament lamp. The PD is 4.2 and the current is 0.34. So the resistance is going to be V over I, 4.2 divided by 0.34. 4.2 divided by 0.34. That gives us 12.3 345 and so on. That is 12 ohms. So the answer is 12. A piece of conducting putty of constant resistance is formed into a cylindrical shape. The resistance R between its flat ends is measured. Its flat ends shaded is measured. The same volume of putty is reformed into cylinders of different lengths L, and the resistance R between the flat ends is measured for each value of L. Which graph best describes the variation of R with L? So we know that resistance is equal to rho L over cross-sectional area. The same volume of putty is reformed into cylinders of different lengths L. That means by all means the cross-sectional area is decreasing, because for the same volume, if it means the length changes, the length must either increase or decrease, the cross-sectional area must change. And volume is equal to cross-sectional area times length, but the volume is the same, so this one is the same. The length is changing, cross-sectional area is changing, so that means when L increases, cross-sectional area must decrease for the same volume. Which graph best shows the variation of R Which graph best shows the variation of R with L? I can even go and substitute there. I can go and substitute there R with L because the volume is the same. Okay, so first of all, because the length increases, cross-sectional area decreases, and when area decreases, resistance must be increasing. So that means A is wrong. This means constant resistance. This relationship is not linear, so that means this is wrong. And this one shows resistance increases and then it is turning to becoming constant as L increases, so that will not be true. The resistance continues increasing infinitely as L increases, because as length increases infinitely, cross-sectional area decreases. As cross-sectional area decreases, the resistance continues increasing. Therefore, our answer is going to be D. Diagram shows the symbol for a component that may be used in an electrical circuit. Of course, this is a buzzer. That is a buzzer. If it was a loudspeaker, I think we use this for a loudspeaker. So many people confuse that with a loudspeaker, but we use this for a loudspeaker. Which law correctly describes Kirchhoff's laws? First law, it must be sum of currents into junction equals sum of currents out of the junction. So this is fine. Sum of currents entering a junction equals sum of currents leaving. So these two are fine. That means this one and this one are not first law. Physical principle, first law is conservation of charge. So it means we have also eliminated this one, because this one is saying conservation of energy. So using the first and second columns, the answer is precisely A. Conservation of charge, of course, for the second law, sum of EMFs around any closed loop in a circuit equals the sum of PDs around the same loop. It is conservation of energy. So the answer is A. A potential divider circuit is formed by connecting a battery of negligible internal resistance in series with the two variable resistors as shown. Okay. The variable resistors have resistance Rx and Ry. Vx is the PD across the variable resistor of resistance Rx. Rx and Ry are both changed at the same time. Which combination of changes must cause Vx to increase? For Vx to increase, Rx must increase and Ry must decrease. Rx must of course increase, must be greater. It's because PD is equal to I times R. If Rx increases, PD is going to be greater. But it will only be greater if Ry is becoming smaller, because if Ry also becomes bigger, then there will be a challenge there. So we are saying Rx must be greater, Ry must be smaller. So the answer is going to be B. The current I in a metal wire is given by that equation. What does the symbol N mean? That is number density of charge carriers, number of free electrons per unit volume. So number of charge carriers per unit volume, that is D. A cell of negligible internal resistance is connected to resistors R1, R2, and R3 as shown. The cell provides power, the circuit, and power is dissipated in the resistors. Okay, so we notice, or we know, that power is equal to V squared over R. The power here is going to be V squared over R1. The power here is going to be V squared over total resistance here is R2 plus R3. Okay, which word equation must be correct? Power in R1 is power dissipated in R2 plus power dissipated in R3. That is not true. That is not true. Power dissipated in R1 is V squared over R1. Power dissipated in R2 is V squared over the sum of the resistances, and I don't think that power is going to be the same, because which word equation must be correct? Is there a negligible internal resistance? Okay, so this is not going to be correct. Power dissipated in R2 is equal to power dissipated in R3. That will depend on the magnitudes of R1, R2, and R3. Although the current will be the same, the PD will not be the same, so that is not correct. The reason as to why this is not going to be correct, there is nothing showing that R2 plus R3 gives us R1. Otherwise, it would be A would be correct. Power output of the cell is power dissipated in R1 plus power dissipated in R2 plus power dissipated in R3. That would be correct, because total power dissipated, total power output from the cell would be the total power given to the external circuit, which will make C to be correct. Power output of the cell is the same as power dissipated in R1. That is not true, because there is some power dissipated in R2 and R3. So the answer is C. A fixed resistor and a diode are connected in series to a battery of e.m.f 6 volts and negligible internal resistance. So this is the fixed resistor and the diode. The PD, the current is the same. And this is a graph for PD of V of the current, I for the diode. So since the current is the same, the current is 40 milliamperes. We can estimate this value here for the PD. And I think if this is 1.25, this is most likely going to be 1.2. So this is most likely 1.2. This one is 1.2 volts. Okay, what is the resistance of the fixed resistor? So the current is the same. We now know that the PD across the diode is 1.2 volts, so this is 1.2 volts. That means the remaining PDs across the resistor. So the PD across this one is 6 minus 1.2, which is going to be 4.8 volts. That is the PD across the fixed resistor. Now we can find R, which is V over I. So that is 4.8 divided by 40 times 10 power negative 3. So that is 4.8 divided by 40 exponent negative 3. So that is 120 ohms, making our answer to be option B. Okay. An electrical cable consists of 7 strands of copper wire, each of diameter 0.3 millimeters, connected in parallel. The resistivity of copper is 1.72 times 10 power negative 8 ohm meters. The current in the cable is 13 amperes. What is the potential difference between 2 points on the cable, distance 1 meter apart? So there are 7 strands. Let me try to sketch this and we see. So we have 1, 2, 3, 4, 5, 6, 7. So there are 7 strands connected in parallel. Okay. Each of diameter 0.3 millimeters connected in parallel. The resistivity of copper is given. The current in the cable is 13 amperes. Okay. So I'll use this space here. I hope I don't have enough space, but I'll try to fix here. So we know resistance is equal to rho L over cross-sectional area. They gave us the diameter. So I'll find the resistance, total resistance, because they're in parallel. I'll find the resistance of 1 first. So resistance of 1 is going to be equal to rho, which is 1.7 times 1.72 times 10 power negative 8 times the length. The length of 1, 7 strands. What is the potential difference between 2 points on the cable, a distance 1 meter apart? So that will be times 1. Then divide by the cross-sectional area, which is diameter, which is pi d. Diameter is 0.3 times 10 power negative 3 squared, divided by 4. I'm trying to find the resistance of 1 strand. So this is going to be 1.72 exponent negative 8, of course, times 1 divided by, the 4 goes up, so I'll say times 4, divided by pi into brackets 0.3 exponent negative 3 squared. So it means the resistance of one strand is going to be equal to 0.24, which value is that? 0.243, 0.243 ohms. That is one strand, but there are 7 and they're in parallel. If they're in parallel, remember resistance in parallel is given by the reciprocals. But because they are identical, total resistance 1 over total resistance in parallel is equal to the number of resistors in parallel if they are identical times 1 over the resistance of 1. So that means we shall say 7 times 1 over 0.243. Then we get the reciprocal. So total resistance is going to be equal to 0.23 divided by 7. 243 divided by 7. So this is going to be divided by 7. So this gives us 0.03476. 0.03476 ohms. That is total resistance. What is the potential difference between 2 points on the cable a distance 1 meter apart? Now we want PD. We have the current in the cable. So PD is going to be I times R, which is going to simply be, the current is 13 times that, so that is times 13, which gives us 0.45. So this is 0.45 amperes. So the answer is going to be C. The I's current is 13. We have been getting total resistance, so the answer is 0.45. A cell that has internal resistance is connected to a switch S and a variable resistor. A voltmeter is connected between the terminals of the cell as shown in the figure. When switch S is open, the voltmeter reads 1.5. So this is e.m.f. e.m.f is 1.5. The switch is then closed. The variable resistor is adjusted to a value of 4 ohms. The voltmeter reads 0.75. That is a potential terminal PD. What is the internal resistance of the cell? What is the internal resistance of the cell? So it means terminal PD, I'll call it V capital T, terminal PD is going to be 1.5 minus 0.75, which is 0.75 volts. That is terminal PD. The current in the cell, or the current is going to be the PD, which is 0.75 divided by the resistance there, which is 4 ohms. That is the current through this, which is going to be the same current through the battery. 0.75 divided by 4, which is, I'll just say the current is that. There is no problem with changing. So the current is that. And also remember, the lost volts or the e.m.f is equal to the terminal PD minus the lost volts. So the e.m.f, which is 1.5, is equal to the terminal PD, which is 0.75, minus the lost volts. But the lost volts is given by current times the internal resistance. So it means the lost volts, so we collect like terms. So this is going to be 0.75 equals to no, this is supposed to be plus terminal PD plus the lost volts. It is the terminal PD which is EMF minus the lost volts. So this is plus. So this is going to be 0.75 equals to the current, which current is 0.75 over 4 times internal resistance R. And you and me notice that the internal resistance, because we cross multiply, it becomes 4. So internal resistance is 4 ohms, which makes our answer to be precisely C. A set of EMF E and a negligible internal resistance C is connected into a circuit as shown in the figure here. The voltmeter has a high resistance, so no current flows through the voltmeter. So let's find the current. This is I, this is going to be I1, this is going to be I2. So it means I2 is the same current flowing here because the current here is 0. I2 is the same current coming here because the current there is going to be 0. Okay, so let's put in the loops. I'll put loops which are clockwise. For the first one here, we have that the EMF E, that is sum of EMFs, is equal to sum of potential drops, which will be 12 times I1, because the current is in the same direction as the loop, so it is 12 times I1. Then I put another loop here in the same direction. One of my students said or argued that whenever you choose loops in the same direction, it means it becomes easy to solve. Maybe. So here there is no cell, so the EMF is 0. Sum of potential drops. The current here is in the opposite direction to the loop, so it will be negative 12 I1. The current here is in the same direction as the loop, so it will be plus 2 I2. The current here is in the same direction as the loop, so it will also be plus 4 I2. But remember, 12 I1 is E, so I'll say 0 is equal to negative E plus 2 plus 4, that is 6 I2. So it means that I2 is going to be equal to E divided by 6. So now I want the PDR, the reading of the voltmeter is the PDR across 4 ohms. So V across 4 ohms is the reading of the voltmeter, which is going to be I2 times 4 ohms. That is current times resistance. So the current I2 is E divided by 6 times 4. So in other words, is 4E divided by 6. Now I want the ratio. So the ratio is going to be equal to V out, which is this, V out, which is 4E over 6 divided by E, which is the same as times 1 over E. And this gives us 2 divided by 3 because E cancels. And then that is 2 over 3, which makes the answer to be D. A battery is connected to a potentiometer. The potentiometer consists of a uniform resistance wire and a sliding contact P. The potential difference V between the sliding contact P and end Q of the wire is measured using a voltmeter. The sliding contact P is moved from Q to R of the wire. Sliding contact P is distance D from Q. Which graph shows the variation with the distance D of the PDV? Of course, when I bring the sliding contact here at Q, when distance is 0, it means the potential difference is going to be 0. It means there will be no potential across the voltmeter because you have brought, they actually are the same potential. There's no difference in potential, not to be giving any difference in potential between 2 points. So that means This one is showing when D is 0, there is a difference, there is a potential difference. So these two are wrong. They are showing when D is 0, there is a potential difference. Then we remain with A and B. We remain with A and B. Remember that potential difference is directly proportional to resistance. It is also directly proportional to the length, because PD across Q, P is going to be a constant, which we call the PD per centimeter, times the length L. So that means V is directly proportional to L, or V is directly proportional to distance from Q. Therefore, this is going to be a straight line. So the answer is going to be A. Which two units are used to define the volt? The coulomb. So the coulomb is a unit of charge, and charge is equal to I times T. So the coulomb is going to be ampere times second. So this means the answer is going to be A. Okay, let part 1 of electricity stop here. We meet in part 2. Bye bye.